Hi there, I'm Floris, and since I don't know when you will be watching this video, first of all, good morning, good afternoon, good evening, or even good night. Today I will present you the content of a paper titled Computable Randomness is about more than probabilities, which I wrote together with Jasper de Bock and Gert de Cooman. I'm a PhD student associated with Ghent University and doing research at the research group Foundations Lab for Imprecise Probabilities. These are my colleagues. The two guys on the left are my two supervisors. The four guys on the right are my four fellow PhD colleagues. In our research group, we develop methods to deal with uncertainty in more general ways. And our three main research topics are imprecise stochastic processes, choice functions, and imprecise randomness. And it's this last topic I work around. So, computable randomness is about more than probabilities. What is it about? The main question that we study, and it's a question I would very much like to let you think about, is the following. Which data sequences do we consider to be random? Namely, how to mathematically describe a random sequence, how to give a definition for randomness. Now, first answer to that question that was given a long time ago, it's called church randomness. And according to this notion, we study infinite binary sequences that are generated by tossing a fair coin. A fair coin with probability a half for 0 and probability a half for 1. And this notion of randomness is built on one very specific observation, the one of convergence of relative frequencies, the law of large numbers. So when considering an infinite sequence, we will require that the relative frequency of 1 along the sequence converges to half. This definition does of course not suffice, otherwise we'd also consider the infinite sequence 0, 1, 0, 1, etc. to be random because the relative frequency of 1 along this sequence also converges to a half. Hence, we will not only impose this property on the whole sequence, but also on some subsequences. For example, we can consider the subsequence by selecting or considering only the elements at odd positions, and impose or require that the relative frequency along this subsequence also converges to a half. We will not consider all subsequences, otherwise we would always be able to only select the ones out of an infinite sequence, which would lead to a relative frequency of 1 instead of a half. Hence, we will look at a specific set of subsequences, and they are defined by computably selectable infinite subsequences. So these are the subsequences that we will look at. Now, what it does mean that some mathematical object is computable, I won't give a rigorous definition of that, but intuitively you can remember that an infinite subsequence is computable when there exists some finite algorithm that can compute it. Now, according to the notion of church randomness, an infinite sequence then is church random when the sequence itself and all computably selectable infinite subsequences satisfy the law of large numbers. Now, this definition has some flaws from the statistical point of view, namely, why should a random sequence only have the property of frequency stability? Now, to tackle this problem or issue, a researcher thought about different or other definitions of randomness, and one of those definitions is called computable randomness, which is developed by Peter Schnorr. And on his account, randomness is really about betting. Now, to understand his definition, I will first need to introduce some mathematical objects. So let us start with that. So we will consider an uncertain event that can take on the values 0 and 1, which are collected in the sample space denoted by curled x. The uncertainty of this uncertain event is described by a probability mass function, which is a map from the sample space towards the real numbers, such that the probability of each outcome is non-negative and such that all probabilities sum to 1. Now we can bet on such an event by giving a gamble, which is a map from the sample space towards the real numbers. And then the expected gain of a gamble with respect to a probability mass function equals just the scalar product between the probability mass function and the gamble. Now we can use these objects to introduce a betting key. So we'll play a little game between two players, forecaster and skeptic. Forecaster, that's me. Skeptic, that's apparently my girlfriend. So they will play a betting game on a random variable denoted by capital X that can take on the values 0 and 1. So the betting game starts with forecaster, who specifies a probability mass function, which describes his uncertainty for the random variable. Next, a skeptic will select a gamble, which leads to an uncertain reward f for herself and minus f for forecaster. However, she will not be allowed to select any gamble. She will only to be allowed to take those gambles for which forecaster expects a positive gain. Hence, the expected gain for the gamble minus f is non-positive, non-negative, I mean, or equivalently, the expected gain of the gamble f is non-positive. Afterwards, the outcome x is revealed, and a reward f goes to skeptic, and a reward minus f goes to forecaster. Now, this idea of a betting game, we will use that to introduce a notion of randomness for an infinite subsequences. And to come to that point, we will not just consider a betting game on one single random variable, but we will consider a betting game on an infinite sequence of random variables. So this betting game will again start with forecaster, who specifies or forecasts a probability mass function, which now describes his uncertainty for each single random variable. Next, skeptic needs to specify her betting behavior. Now, in this case, she does not just need to specify one single gamble for a random variable, but we will require her to specify her betting strategy on the whole event tree. Namely, she needs to specify her gambles for a certain random variable, given that some finite sequence of outcome has occurred. Now, what do we mean by that? So, consider, for example, that we start with the initial situation that we denote by this little square. Then she will put the gamble f square on the random variable x1. Next, when the outcome 0 occurs, she will put the gamble f0 on x2, but if the outcome 1 occurs, she will put the gamble f1 on x2, etc. With this betting strategy that she defines on the whole event tree, corresponds a capital process. Namely, if we consider a specific finite sequence of outcomes, such as 0011, then her capital, which we will denote by this letter, corresponds to her initial capital, which we'll denote by this symbol, plus the gain or loss that she suffered from along this sequence by adopting her betting strategy. So with her betting strategy corresponds capital processes, and we will furthermore impose that all her capital processes along every possible finite sequence of outcomes is non-negative, which prevents her from borrowing money whilst gambling. And furthermore, we will require that her betting strategy is computable, namely that there exists a finite algorithm that competes for each possible finite sequence of outcomes, which bet she will put on the next random variable. And now when considering some infinite sequence, we will consider it or call it computably random when skeptic has no computable non-negative betting strategy that is in line with the probability mass function that the forecaster specified, by which she can get infinitely rich along the sequence. So that defines computable randomness. As I already hinted at, computable randomness strengthens the notion of randomness with respect to church randomness, and hence all computably random sequences are also church random, which means that a computable random sequence also satisfies the law of large numbers. Now, these classical notions of randomness actually suffer from a problem. Namely, according to these notions of randomness, random sequences typically satisfy the law of large numbers. Now, there are many physical processes which do not satisfy this law of large numbers, and this has been rigorously stated by Igor Gorban, who has even written a book about this, titled The Statistical Stability Phenomenon, in which he studies a variety of processes in the field of meteorology, astrophysics, noise, etc., for which he proves that they do not satisfy the law of large numbers. Now, this issue has recently been addressed. Um, In a paper by Jasper and Gert titled "Computable randomness is inherently imprecise." And in this paper, they noticed that the classical notion of computable randomness is always defined with respect to a precise probability mass function, P. What they do in their paper is they extend this notion of computable randomness by developing a notion with respect to a probability interval, which is a more general model to describe your uncertainty, instead of with respect to a probability mass function. Now, in this paper, we extend their imprecise notion by creating a notion of computable randomness with respect to a coherent lower expectation, which is an even more general uncertainty model. And we allow the sequences to take values in a more general sample space, namely the sample space can have any finite size instead of just 2. Now, to introduce our notion, hence we will again look at random variables that can take values now in arbitrary finite sample space. For ease of visual representation, we adopted a ternary sample space which contains grapes, cherries, and bananas, and we will again put bets on this random variable. Now we will describe our uncertainty not by looking at the precise probability mass function, but we will look at the closed set of probability mass function, which is intuitively indeed much more general with respect to just a precise probability mass function. And with this closed set, we will now not correspond or connect an expected gain, but a coherent lower expectation of a gamble f. And a coherent lower expectation with respect to this closed set of a gamble f is now the lower envelope of the expected gain of your gamble f based on all probability mass functions that are element of your closed set. Equivalently, we can introduce a conjugate upper expectation, which is defined as the conjugate upper expectation of a gamble f equals minus the coherent lower expectation of minus the gamble that you consider, and this corresponds with the upper envelope of the expected gain with respect of all probabilities mass functions that are element of your closed set. Now, when in limit, when we consider just one precise probability mass function, the coherent lower and upper expectation just correspond with a precise expected gain, which is the most informative way to describe your uncertainty. However, when we describe our uncertainty in a most uninformative way, then we adopt the complete set of all probability mass functions, which we will denote by the vacuous closed set. With this vacuous closed set of all probability mass functions, the coherent lower expectation takes on the form of just the minimum of f, and the conjugate upper expectation of a gamble f equals then the maximum of a gamble f. Next, we will be able to use this more general uncertainty model to again look at a betting game. Namely, we will again consider a game between two players, forecaster and skeptic, who will bet now on the random variable x, which can take values in a ternary sample space. So forecaster will again start with forecasting a coherent lower expectation. Next, skeptic will again select an uncertain reward f. She will again not be allowed to just take any gamble. She will only be allowed to take those gambles with a non-negative lower expectations, which is equivalent to a non-positive upper expectation f. Afterwards, the outcome will be reviewed, leading to a reward f for skeptic and reward minus f for forecaster. Now we will again use this betting game on single bets to bet on an infinite sequence of random variables. So we again consider an infinite sequence of random variables. The forecaster again states an uncertainty model, which is now a coherent lower expectation, which describes this uncertainty for each single random variable of the sequence. Next, the skeptic will again state her betting strategy on the complete or the whole event tree by stating several gambles. With this betting strategy, there corresponds again some capital process with each possible finite sequence of outcomes. We will again impose that a betting strategy corresponds with non-negative capital processes in order that she's not able to borrow money, and we also impose that her betting strategy is computable. So in our case now, an infinite sequence then is considered to be computably random with respect to coherent lower expectation, when a skeptic has no computable non-negative betting strategy in order to become infinitely rich along this sequence. So now we have a definition, a more general definition of computable randomness. Does it make sense? Yes, it does make sense because we can look at its limit behavior, namely when we look at our definition and only apply it to sequences, infinite sequences that can take values in a binary sample space, then we can prove that our definition coincides with the definition as developed in 2017 by Jasper and Gert. And when we even impose stronger conditions on our definition that we are looking at, namely if we again only consider binary sequences, but now only look at a precise probability mass function, then we can also show that our imprecise definition in that limit case coincides with the definition in a precise classical case. So, what other properties does our definition entail? First of all, we have proven that for every coherent lower expectation, there is at least one infinite sequence that is computably random for it. Conversely, we can ask the question whether for every infinite sequence there is at least one coherent lower expectation for which it is computably random. The answer to the question is yes. Indeed, when forecaster forecasts the vacuous coherent lower expectation, then skeptic will only be allowed to take those gambles with a non-positive upper expectation, which in this case for vacuous coherent lower expectation is similar to the maximum of your gambles being lower than or equal to 0, and hence the capital that skeptic can build up is bound above, namely she can only suffer loss. And hence there is no way for her to become infinitely rich along any infinite sequence. Now, furthermore, or thirdly, we have proven that for every infinite sequence that is computably random with respect to a coherent lower expectation E, it is also completely random with respect to any coherent lower expectation E accent that is more conservative in the way that for every gamble F, the coherent lower expectation E accent of the gamble is smaller than or equal to the coherent lower expectation E of the gamble. Indeed, when E accent gives a smaller coherent lower expectation for every gamble, this means that a forecaster will allow skeptic to choose from less gambles, since he expects more gambles to have a non-positive payoff, and hence skeptic's freedom is indeed reduced. The possibility for her to become infinitely rich is decreased. Next, we have also proven a property about convergence of relative frequencies, namely when an infinite sequence is completely random with respect to a coherent lower expectation, and you consider a specific gamble f, then the running average of this gamble, first of all, of course, lies in between the minimum and the maximum of the gamble that you consider. But furthermore, the lim inf and lim sub of the running average do not need to converge anymore, but they always need to lie in between the coherent lower and coherent upper expectation of the gamble that you consider. Now, as a wrap-up, I've created an overview of the striking differences between the precise and imprecise case. Namely, in the precise case, running averages of a computably random sequence always converge. However, in the imprecise case, the lim inf and lim sub not necessarily need to fall together. Furthermore, in the precise case, not all infinite sequences are completely random with respect to a probability mass function, but if an infinite sequence is completely random, then this probability mass function is unique. In the imprecise case, however, all infinite sequences are completely random with respect to the vacuous coherent lower expectation, And if an infinite sequence is completely random with respect to some coherent lower expectation E, then it is also completely random with respect to any coherent lower expectation E extant that is more conservative. And these properties let us wonder in the imprecise case. So if an infinite sequence is completely random with respect to some coherent lower expectation E, then it is also always completely random with respect to any coherent lower expectation E extent that is more conservative. Hence, is every infinite sequence completely random with respect to some least conservative coherent lower expectation? Unfortunately, we cannot yet answer that question. We, however, conjecture that the answer is yes. But we can provide an answer when we change our attention to a different uncertainty model. Um, so which uncertainty model will we adopt then? So in the classical case, there is a definition of computable randomness with respect to a probability mass function. In the imprecise case of 2017, there's a definition with respect to probability intervals. In this paper, we have introduced a definition with respect to coherent lower expectation. Now, we will fill the gap between probability intervals and coherent lower expectations by now introducing a definition of computable randomness with respect to a gamble f and an expectation interval I. So we'll first introduce this definition. So an infinite sequence is now computably random, not with respect to a coherent lower expectation, but with respect to a gamble and expectation interval I, if there exists a coherent lower expectation for which this infinite sequence is completely random, such that the coherent lower expectation of the gamble that you're considering is equal to the left bound of your expectation interval I, and similarly, the conjugate upper expectation of this coherent lower expectation for the gamble f equals the right bound of your interval. So this is quite an indirect definition. So which properties does this definition entail? First of all, similarly to the previous case, for every gamble and expectation interval I, there is always at least one infinite sequence that is computably random with respect to it. Secondly, all infinite sequences are computably random with respect to the gamble f and the vacuous expectation interval. Indeed, this holds because, as I have shown before, all infinite sequences are completely random with respect to the vacuous coherent lower expectation, and the vacuous coherent lower and upper expectation equal the left and right bound of this vacuous expectation interval, respectively. Furthermore, we have proven that if some infinite sequence is completely random with respect to a gamble f and expectation interval I, then it is also completely random with respect to this gamble f and any expectation interval that contains any expectation interval I extent that contains this expectation interval I. So we now know that if we consider an infinite sequence and a specific gamble, then that the infinite sequence is completely random with respect to the vacuous expectation interval. We also know that if it is completely random with respect to an expectation interval I, then it is always completely random with respect to any expectation interval that contains this smaller expectation interval. But now still, the open question remains, namely, is the infinite sequence completely random with respect to some smallest, some most informative or least conservative expectation interval? And now we can answer that question positively, namely, we have proven that for every such sequence and every gamble, we can define two intervals, an interval LF and interval UF, which can both be half open or closed, such that every infinite sequence is completely random with respect to this gamble and an interval if and only if the left and right bound respectively lie in this interval LF and UF. So for example, this interval, well, the infinite sequence will not be completely random for this interval because its left bound is not an element of the interval LF. And this completely characterizes for a single gamble the computable random character of one specific infinite sequence. To exceed my time limit not too much, I will just end by focusing on a single question, namely, why is this abstract chisel relevant and could it ever be used? Now, to answer those questions, associating uncertainty models with data actually functions as the basis for doing statistics. And since there are processes that cannot be described by just adopting conventional statistical methods, because we have seen that relative frequencies do not always tend to converge, we are convinced that the results in our paper can function as a point of departure for development of completely new types of statistical methods that learn more imprecise uncertainty models from data. And this way, we will create more reliable statistical methods in the sense that they do not insist anymore on associating a precise probability mass function with a data sequence. Now, this is it for me now. I very much hope to see you at the Q&A.